Hi, everyone. In this video, we'll introduce some preliminary notions that will be important to our study of analysis of functions of several variables. In particular, we want to begin to understand the types of functions we will be working with, as well as some of the basic structures of the Euclidean space Rn, which will help us understand how these functions behave. So to begin, we want to distinguish between two different types of functions of several variables, between a scalar field, which is a function from Rn into R, and a vector field, which is a function from Rn to Rm. Now, we will generally be thinking about these such that n and m are both greater than 1. So here, we're really thinking about a function which has as its input either n variables. So one way to think of this is a function whose input is n variables and whose output is a single real number. Or alternatively, you could think of this as a function whose input is a vector in Rn and whose output is a scalar in R. When we talk about a vector field, we're again thinking about a function whose input is a vector in Rn or is n variables, but now we're thinking about it having an output which is either a vector in Rm or is m distinct outputs, right? So as examples of these, when we think about a scalar field, one way to think about and to visualize this, and I think it's nice to start this course with drawing some pictures. Pictures will be helpful to us. Sometimes we'll be able to draw them on the board. Other times we'll utilize technology to help us. Usually when I'm just thinking about a function from R to R, right, I have my domain here and I have my range here. But now if I'm thinking about a function from Rn into R, and let's maybe make this a little easier by thinking about a function from R2 into R, I need my domain space not just to be R anymore, I need it to be R2. I need it to be a plane. So I'm going to sort of add here these arrows. So I'm thinking of this as having like input values X and Y. So you can imagine that my domain here is now represented by a plane which extends sort of perpendicular through the board here, right? And through this line, okay? So I have my two input values, X and Y, and then I have some output, which I'm going to represent, say, by T of XY, right? And my output from this scalar field T is a single variable. So I could take some examples. So for example, maybe T of XY is equal to X squared plus Y squared. And so what I can imagine doing is taking a particular pair of X and Y values, right? So maybe I take X is equal to 1 and Y is equal to 1. So I come over here to the point 1, 1 in my domain. Okay, so this is the vector 1, 1 in my domain. And then I plug those in. So 1 squared plus 1 squared gives me 2. And so then I go up, and the height of this point, which now it lies on the surface of this function, is 2. Okay. And for this particular scalar field, if I was to do this, I would get a surface that looks like something like this. So looks something like this. Okay. So we call this a paraboloid. Sort of imagine you take a parabola in the plane and just rotate it around this z-axis now, and this gives you this sort of figure. So again, this point is on the surface precisely because when I plug in x is 1, y is 1, that maps up to the point 2. And so this point, this point 1, 1, 2 lies on this surface because this is just x comma y comma t of x, y, right? Just like when we graph a function in the plane, right, we plot the points x comma f of x, and that collection of points for all x in the domain of f gives me the graph of that function. Now, in practice, what are some examples of scalar fields? Well, imagine, for every point on the globe, other than the poles, we can talk about the latitude and longitude of those points. So you can imagine at each latitude, longitude point, right, on Earth, you could go and measure the temperature. So that gives you a scalar field where your inputs are the latitude and longitude, and your outputs are the temperature at that particular point. Now, when we transition to a vector field, we're still thinking of multiple inputs, right? But now, instead of having a single output, we have multiple outputs. So back to sort of some examples in that latitude, longitude. Imagine you went to each point on the globe, but instead of measuring the temperature, you measured the wind speed and direction, right? So that gives you sort of a vector. The wind's velocity vector would be a vector in R2 or R3, depending on how you want to measure it. But that would give you a vector output at each vector point on the globe. So you have multiple inputs, sort of your latitude and longitude, and multiple outputs, which are the vector components of your wind velocity. Okay. Now, when we go to represent vector fields, let's say if we were thinking about a vector field, say from R2 into R2, one way we might think about that is to draw all of R2. So this is going to represent, this plane is representing my domain. And then at each point in my domain, I could draw sort of the little vector output, right? So this vector here, if this is the point, say x naught, y naught, then this vector drawn here is t of x naught, y naught. Now, I've intentionally called these t to point out that one of the issues that pops up is that sometimes without more context, it can be difficult to tell, is t of x naught, y naught a vector or a scalar? Now, when we're clearly in the case of, okay, I've declared that t is a scalar field, then over here, t of x naught, y naught would have to be a scalar. Over here, when I've declared that t is a vector field, then clearly t of x naught, y naught will be a vector in Rm. But if I'm just sort of out in the wild and I happen to see, say, t of x naught, y naught, I might wonder, is that a vector or a scalar? I don't know what type of function this is. Now, there are different ways that different authors will choose to denote this. So sometimes, for clarity, we may put a vector symbol over the t. Now, note that that does not mean that t is a vector. T is not a vector. T is a function. But this helps us recognize that t of x naught, y naught, right? When I evaluate the function at a specific point, I do get back a vector. So this is just some notation to help us represent that this function t really, in fact, is a vector field. Alternatively, something that you can't do very well on a chalkboard, but you can do in print, is oftentimes things that are vectors or vector valued may be written in bold. So, for example, I could, instead of thinking about these points x and y separately, right? Instead of thinking about x naught and y naught, I could think about representing this point in my domain as some vector x. Okay. And so then I look at what happens to t when I plug in this vector x, and that gives me back another vector. Okay. So one of the difficulties sometimes with reading this and working with it is there are lots of different notations that all mean the same thing. Now, to put your mind at ease a little bit, often context will make it clear what things are meant to be vectors and what things are meant to be scalars. We often begin proofs with, let t be a function from Rn to Rm. Okay, great. If that's the case, I know t is a vector field, right? Or let t be from R3 to R. Okay, great. Now I know that t is a scalar field. But sometimes when you're just in the middle of a proof or something, it can be a little difficult. Or if you're reading the textbook and the reference to t is going on for a while, it's easy to forget. So some of these notations help remind us. Now, visualization of functions of several variables is difficult. My guess is that many of you have encountered this at some point taking a Calc 3 course. And if it's been a while since you took that Calc 3 course, you could encounter some difficulties moving forward. Thankfully, at least since I first took Calc 3, visualization software has come a long way. Desmos in particular now has a a pretty functional online tool to visualize functions of several variables, and we'll be using that to help visualize some things throughout the course, along with other kinds of mathematical computing software. So I would encourage you, if you aren't familiar with the Desmos 3D plotting, to log in. Just start plotting some different surfaces. Play around with it a bit to get comfortable with it. Again, as we move forward in this course, I will give you opportunities to utilize that, and I will utilize it in some of the lectures as well, but just something I encourage you to do as we start to get our bearings in this course. Now, one of the things you'll notice is that, actually, if I flip back slightly here, right, the big change we've made from Math 5610 is that now our domain is no longer just R, or no longer just a subset of R. It's now Rn, or some subset of Rn. Okay, and in order to understand things, if you think back to 5610, we spent a long time just trying to make sure we really understood some things about R, not because it was the range so much as because it was the domain. So think for a second about the definition of a limit of a function from R to R. One of the first criteria we needed to check was that the point where we were trying to take the limit was an accumulation point of the domain. Okay? Well, if we want to understand anything about limits for these types of functions, we're going to need to define what it means to be an accumulation point of Rn, or what it means to be an accumulation point of some subset of Rn. Well, you start following things back, you realize we need to do a little work. We need to first just understand how are we going to measure distance in Rn. Now, you may have seen this before, but we want to sort of understand it at a slightly deeper level and also see some connections between it and other quantities. So when we talk about the n-dimensional Euclidean space Rn, right, we're just thinking about the set of all ordered n-tuples of real numbers. So we often will represent a point in Rn by a boldface X here, right? Or maybe an X with a vector arrow over the top of it. But really what I'm thinking here is, right, there is a first component, a second component, a third component, all the way up to the nth component. So that's the ordered part. And then I'm imagining that x1, x2, x3, all the way up to xn, each of those is itself a real number. Okay, so I have n components. We call these components, or sometimes coordinates. Each of these is a real number, and each of them is assigned a specific place in the vector, right? So, for example, right, 1, 2, 3 is a different vector from 2, 1, 3. Even though they have the same entries, this is in the first component, this is in the second component, this is in the third component. Here, the first components are different, so these are different vectors. Now, you can already see the book is going to use the notation 1, 2, 3 like this for a vector. 2, 1, 3. Some other sources will use vertical entries. These all mean the same thing. They're all just notation for keeping track of what's the first component, what's the second component, what's the third component. Okay. Now, I'm going to switch back and forth from time to time between notations, in part because if you end up teaching a Calculus 3 course, which is part of what, this course is designed to teach you to be able to handle, teaching a Calculus 3 course. If you ever teach one of those, as you switch from book to book, the notation can change wildly. Okay, so I want you to be comfortable with and familiar with several different kinds of notations, and I will intentionally change notations from time to time, both here in the lectures. I'll probably keep it like the slides will be fairly consistent with the text, but on homework problems, I might represent things slightly differently. That is to get you accustomed to those different types of representations. If at any point you have a question, reach out to me. That's not necessarily meant to be the tricky part. It's just something I want you to become comfortable working with over the course of the semester. Okay. So we have this space Rn. Right now, this is just a set, right? It's the set of all n tuples of real numbers, right? Now, of course, we can think about the R1, right? That's just the line, right? That's just the real line, right? It's a set of all 1 tuples. R2, right? That's just the plane. R3, right? We can sort of represent this, okay, the set of all three tuples, right? R4, right, beyond R3, it's very, very difficult to visualize things in R4 and higher. Now, we may talk occasionally, there are some tricks that are occasionally helpful to thinking about things in R4. Sometimes you can think of them as like things in R3 that are evolving over time. So time becomes like the fourth dimension. Certainly beyond that, visualizing things in higher dimensions is very difficult. But so we have these sets for the time being. These are all familiar sets that you've seen before. But we now want to look at some more structure on these sets, right? The sets in and of themselves are not actually particularly interesting from sort of a set theoretic point of view. They're just collections of n tuples. So we want to see what we can say beyond just the set theoretic structure. So once you have this set, right, and these are sets you've seen before. So you start to imagine, okay, imagine I have two vectors in the plane. Here's u, and maybe somewhere up here is the vector v. You can start to wonder, well, what sort of questions might I wonder about these? And much of this, right, originally is motivated by physics. So just sort of what are naturally occurring questions I might ask? I might wonder about the length of one or both of these vectors, right? So what's the length of u? That's a very natural question to ask. What's the length of v? I might ask about sort of the distance between two vectors. What does it mean to take the difference of two vectors, right? Or just more generally, even if I don't want to know the difference, what about just the distance? Like, what does it mean to measure, say, the distance between these two vectors? So I might wonder about the distance between u and v, right? I might wonder about, once I have two vectors, the way I've represented them here, I might wonder about the angle theta that lies between them, right? So there are all of these very natural geometric questions that pop up in Rn, right? And so we can certainly ask these questions in higher dimensions as well. If I have two vectors in R3, I'll point out that the question about length and distance is fairly straightforward. You'll immediately know, so in R3, if you take two vectors, when you talk about angle, you have to be a little bit careful about what do you mean by angle, right? So you have to think about the fact that these two vectors form a plane, and you're measuring the angle in that plane, right? So, but you can ask these same natural questions. So we want to come up with ways of measuring these things. Now, in what may seem a little surprising, we're actually going to start with thinking a little bit about angle. Now, we're not going to deal with angle directly. The first thing we're going to talk about is what's called an inner product. Now, the inner product of two vectors is related to the angle, and we'll talk about that as we move forward. But for the time being, this is just a quantity we can calculate given two vectors. Now, we are going to use a particular inner product, which is called the dot product. So an inner product is just a function that takes in two vectors and spits out a scalar, okay? And in our particular case, we want to work, and it needs to satisfy some additional properties. In linear algebra, you probably looked at inner products, and you can describe a more general inner product. We just need to really talk about the dot product. So the particular inner product we're going to deal with, called the dot product of x and y, is just defined by, okay, I write x dot y, and that's just going to be equal to, I take the first components of each vector, multiply them together. Take the second components of each vector, multiply them together. Third components, multiply them together. All the way up to the nth components, multiply them together. Then I take each of those products and I add them all up. Okay. So, for example, right, if I have the vector 1, 4, -2, and I want to take the dot product with 0, 2, 1, right? That's just going to be 1 times 0, which is 0, plus 4 times 2, which is 8, plus -2 times 1, which is -2. And that'll give me an inner product of 6, right? So I'm just taking the products of corresponding entries and then adding them all together. Now, again, we'll sometimes, there's, of course, multiple representations for all of this. So This is when we are specifically using the dot product. This is a fairly standard notation. For a generic inner product, we more often use these angled brackets. So we write like the inner product of x and y. Now, it's worth noting, again, the dot product is just one example of an inner product on Rn. Okay, so I don't want to beat this over your head too much, but there is a distinction between dot product and inner product. Every dot product, the dot product, there's only one, is an inner product, but there are many inner products, not all of which are the dot product, right? But the one we're going to use for our purposes, they're going to be synonymous because we're always going to be talking about the dot product. Okay. Now, again, I mentioned the dot product is in fact related to the angle between two vectors. How that works, we'll talk about a bit more as we go along. Okay. Now, it turns out that as soon as you have not just a dot product, but any inner product, if you have an inner product, that automatically induces a norm on your space. Now, what's a norm? Well, a norm is really a way of measuring the length of something in a vector space. Now, again, we're using a particular inner product, the dot product, so we can look at how the dot product induces a norm or a way of measuring length on Rn. So we're going to define the norm of a vector in Rn. So we use this notation, right? It looks sort of like absolute values, but it's just double bars on both sides. And we're just going to define that to be the norm of a vector to be the square root of the dot product of the vector with itself. Now, again, in general, you could define this, even if we weren't using the dot product, you could define this as the inner product of x with itself, take a square root to the 1/2 power. Okay. So anytime you have an inner product on a space, it automatically induces a norm on the space as well. Now, again, for our case, we're just using the dot product as the inner product. So we write out, okay, well, what would the dot product be? Well, you're taking the dot product of x with itself. So you're just getting x1 times x1, that's x1 squared, plus x2 times x2, that's just x2 squared. So you're getting x1 squared plus x2 squared plus x3 squared. Excuse me. So you just end up with this expression here. And if you look at this, you may notice this is the standard Euclidean norm, right? This is how you learn to measure the norm of a vector in like an introductory linear algebra course. This is just the standard Euclidean norm. So that dot product, which is an inner product, every inner product induces a norm. That norm in this case gives us back the standard Euclidean norm. So the dot product is the inner product which induces the norm that is the Euclidean norm. Okay. And then just as a bit of verbiage here, right? When we talk about a vector and that vector has norm or length 1, then we just call that a unit vector. So if we say a unit vector, or in general, if we say a unit anything, that just means that thing has sort of been standardized or normalized to have length 1. All right. Now, once you have a norm, that norm induces a metric. And a metric, if you recall from 5610, is just a way of measuring distance. Okay, so the distance between any 2 points x and y in Rn is just defined as, so here we're defining a metric, d. So the distance between x and y is just the norm of the difference between the vector x and vector y. Again, if we write out what that means, so sort of as an intermediate step, you could think, well, what does this really mean? Well, okay, here, the norm of this vector, that's just the square root of the inner product of x minus y with itself. Okay, then you write out what that would be, you get this. And if you notice, right, this is just the standard distance formula in Rn. Okay, and so we call this the Euclidean metric, right? So what I really want you to take away from this is, I mean, on the one hand, we're going to measure lengths and distances in the way you normally would, okay? But what I also want you to see is that all of this actually flows down from choosing our inner product to be the dot product. And once we choose our inner product to be the dot product, that induces a norm, which is the standard Euclidean norm. That norm then induces a metric, which just gives me the standard Euclidean metric. So when we talk about measuring like lengths and distances and even sort of angles between things, in Rn, our choice of inner product and norm and metric, they're not independent of each other, right? I'm really choosing an inner product and then using the norm and the metric that are induced by that inner product. So all of these things are related, and we shouldn't be surprised that there are going to be connections between those things. All right, well, once we have a way of measuring distance, it actually turns out that we have a way of pretty much recreating all of the sorts of topological things that we saw for R in Math 5610. We can pretty much recreate all of these things by just changing the way we measure distance. So for example, one of the first things we needed to do in 5610, when we wanted to try and talk about an accumulation point, we needed to be able to talk about a neighborhood of a point, right? So in this case, instead of having a point in R, we're going to have a point in Rn, okay? So take a vector A in Rn and some R greater than 0. Then I can define a neighborhood, or we'll also call it an open ball, with center A and radius R, and we can define them in the following ways. Now, these are just two notations that mean the same thing, right? And then what we're going to do over here is, well, what is the neighborhood of radius A around the vector A? It's just the set of all other vectors x in Rn, such that the distance between x and A, right, because this is really just another way of writing distance between x and A, is less than R, right? Now, if you go back to 5610, this is pretty much exactly how we did it in 5610. We just wrote this for the distance, right? Because in R, this is the distance, right? Here we just have a different, slightly different kind of distance, right? But it's still the Euclidean distance, okay? So simply by understanding these inner products and norms and metrics on Rn, we can immediately adjust all of our definitions from 5610 to basically work in the same way. And so we can define a neighborhood here, right? And so in R1, that neighborhood, right, of the point A is just the interval around A. Okay? So visually, if I were to draw this, right, so here's some point A, and my neighborhood of radius R is just going to be some interval around A, where this distance here is R, right? So in R1, or just R, these neighborhoods are just open intervals. But if I switch and move, say, to R2, see, what's that going to look like? Well, now I'm in the plane. I'm in R2. I have some point A. I can think about maybe representing that by like this vector A. Okay, but I'm sort of thinking about this point, and then I'm looking at all the vectors that are within R. So this gives me an open disk in the plane centered at A. Now, if I move up to R3, draw this down here. So now I'm in R3, and I'm going to pick some point A. You can imagine it's sort of maybe sitting up here somewhere. So there's my point A. And now I look at all the x values that are distance R from that. This is actually going to give me some sort of ball. Okay, so we're going to call this an open ball, because this is this. I think the analogy that's most helpful here is to think about a beach ball that's filled with air. The open ball is the air inside the beach ball. It doesn't include the surface. Okay, it's just the stuff inside. So I'm looking at all things whose distance is strictly less than R. If I made this to be the set of all things whose distance was less than or equal to R, then I would have all the air inside and the plastic on the beach ball. Okay, if I made this norm of x minus a is equal to r, then I would just get the plastic of the beach ball, right? So we call just that plastic the sphere. If we're just looking at the inside, we would call that the open ball. That's just the air inside. And if we were looking at the closed ball, that would be the plastic and all the air inside. Okay. But you can see, again, these are all just different takes on the same thing as we change the dimension here, which necessarily changes the norm here. Okay. All right. Well, now that we have a definition of a neighborhood, we can now turn around and pretty well modify all of the sort of topological things that we did in R. Okay. So, for example, right, we could define an accumulation point in exactly the same way. So with this sort of just basic change of metric, all of our topological notions from R are going to pretty quickly generalize to Rn. All the definitions, all the related theorems are going to be pretty much analogous to the corresponding statements on R. So take, for example, right, we defined an accumulation point. So something, like we said, a point A was an accumulation point of S that was defined to be true if for every R greater than 0, the neighborhood of radius R, sorry, the deleted neighborhood of radius R around A intersect S was not the empty set. Okay. Well, that definition is going to be exactly the same in Rn. The only thing that's happened is how we define a neighborhood has changed slightly, right? But it's exactly the same idea. Okay. In fact, the proof is nearly identical, right? The proof of claims about accumulation points, right? All these proofs that you go through, for example, let me give a specific example to make this a little easier. You can also define an interior point, right? All that changes is your definition of neighborhood, right? And we proved, for example, that a set was open, by definition, a set is open if and only if every point is an interior point. And then we showed every neighborhood was open, right? That's a theorem. So the theorem that every neighborhood is open, you prove it in exactly the same way in Rn and R, you just slightly change your definition of neighborhood. So one of the first problems I'm going to give you on a homework assignment is actually to recreate one of those proofs, but just using these slightly modified definitions. Now, while they are very, very similar, there are some important things that have to be dealt with. Namely, you need to be careful about what types of objects you're dealing with. Things that were real numbers, A, are now vectors. Things that were differences or were absolute values of differences are now norms of differences. And one of the things I want you to take care in doing is to start to recognize what things are vectors and what things are scalars, what things are absolute values and what things are norms. Because that will be very important as we move through in recognizing where proofs can largely be the same and where some special care needs to be taken in order to ensure that we are correctly proving things, because now this thing that used to be a scalar is a vector, and I need to be a bit more careful. We'll conclude our discussion at this point for today. The next thing we want to do is use these modified notions of accumulation point and interior. And again, all of this really just gets back to changing the metric. We want to use these to start to understand limits of functions of several variables, which we will do in the next video.